Welcome to I Love Apes. We are in Unit 2, which is all about biodiversity, and today we're going to study a very fascinating topic called island biogeography. It's one of my favorite topics in this unit, so let's get started. So, island biogeography, it's basically the study that looks at how geographical aspects of an island, like how big it is, how isolated it is, how far it is away from, say, the continental mainland, is going to affect the biodiversity of the islands. And so we're going to limit ourselves today to actual islands, okay? So just a piece of land out in the ocean that's separated from everything else by salt water. But the same thing would be true for, say, an oasis in the desert. So I have this essentially an island of plant life in the middle of this ocean of sand, so to speak. It would work for an isolated mountain. So the species I would find here that are isolated from these ones here would follow the same basic principles of island biogeography as would, say, an isolated lake that's far away from other lakes separated by a bunch of land, the way this one is separated by a bunch of water. So the same principles will be true for island biogeography for these different environments, but we're going to limit ourselves today just to islands for the sake of keeping it simple. So here's the basic idea. The biodiversity of an isolated system, like an island, is going to depend really on two main factors. One is the rate at which it is colonized, the rate at which new species arrive on the island from other places. And the other one is the rate of extinction. At what rate do things go extinct on the island? And those two factors combined are going to decide basically how much richness of species we can expect to find on the island. And now that in turn depends on two things. So the isolation of the island from the mainland is going to determine the rate of colonization, and the area of the island, how big it is going to determine the rate of extinction. So those are the core principles of island biogeography. We're going to look at some graphs that could be a little bit confusing, but if you listen to what I'm saying, it's going to make sense. So let's get started. All right, so how do most islands form in the first place? You might not have ever thought of that. They can form other ways. They can form by erosion of the mainland, can leave a piece of the mainland isolated by water. That would be an island. You could have faulting that pushes things up. But in the vast majority of incidences, islands are the result of volcanic activity. So basically, under the ocean, we can have a volcano, a submerged volcano, that's slowly erupting and adding lava to its flanks and getting taller. And eventually what happens is this volcano is going to come through the surface of the ocean. And this has actually been documented. There's a really famous one called Surtsey, where people were out there with cameras filming it as it came out of the ocean. Really cool. Well, when it first comes up, it's just bare rock. There's not going to be any life there. So primary succession is going to have to happen before we can start to colonize. But the term colonize just means arrive at and begin living on. Okay, and so organisms, both plants and animals, are going to arrive at and begin living on the island. So what we'll find then is eventually the island is going to become full of life. I'm really proud of that picture. I love my palm trees, and my little birds. Oh man, I was so happy when I drew that one. I know my artistic skills aren't great, but I was still pretty pleased with myself. So anyway, so that's the idea. These volcanoes come up, you have bare rock, and after some time period of primary succession, we get life. But this life we see here, it came from other places because this island is isolated from all the other life on Earth, at least initially. All right, so what is the main way that these plants and animals arrive at these islands? So I've got two islands here. I've got one that's close to the continental mainland and one that's far away. All right, and the way they tend to get there, we talked about in a previous episode, is by rafting. Birds can fly, okay, but terrestrial organisms, plants and mammals and reptiles, the way they're going to get there is they're going to get swept out to sea during a flood. They're going to cling to some piece of floating debris like a log, and they're going to get blown across the ocean by winds and carried by ocean currents, and they're going to arrive at this island and begin to colonize it. All right, so that's how they get there. The thing is, the closer an island is to the mainland, the more chance the organisms have of surviving the trip, because it's a very arduous trip, right? Salt water is not something that terrestrial organisms are designed to endure. There's no food. There's no fresh water to drink. There's total sun exposure. There's all these things that make it likely that the organism is going to die before it gets here. So that basically it limits how many organisms are going to survive the trip. Well, now imagine rafting this island versus that one. If you were told you have to get to one of these two islands, you can say, I want to go to this one. I'm more likely to survive. So what we find then is the further an island is from the mainland, the fewer organisms are going to survive to begin to colonize it. So we'd expect the rate of colonization, the rate of new arrivals, to be higher on the close island and much lower on the far island. Now, if we plot the rate of new arrivals, and here's where I really want you to pay close attention, because this graph is really weird when you first see it. So we're going to make a graph where we have the rate at which new species arrive on the island by rafting over, and the number of species that are on the island. Okay, not the number of individuals, the number of species. So here's what happens: we have there's nothing on it. So the first species to arrive, at first when you arrive, you're the only one of your species there. So the rate of arrival of new species is going to be very high. But now, let's just say, a few hundred years go by, and another organism of the same species that arrived here, well, it's not a new species on the island. This is the rate of new arrivals, so it doesn't count. So what we're going to find is this rate is going to drop because the odds become less and less that upon arrival you're going to find that you're the only member of your species there. So the rate at which new species arrive on the island is going to go down over time and give us this very distinct downward sloping curve. So you should get used to seeing graphs like this where when you see a curve that starts high on the left and sweeps down to 0 on the right, you're looking at a graph of the rate of new arrivals, new species arrivals. Now, a lot of times on the AP test, they'll say the word rate. They won't say the rest of it. They want you to look at this graph and say, I understand, because I'm starting up here and dropping down. That's the rate of new species. Now, why does it always go to 0? Because there's only so many organisms on the mainland that are capable of making it to the island. And eventually, they're all here. So we can have no more new arrivals. So that's why we're always going to get this curve. Now, we can do something interesting with this curve. So islands that are close to the mainland, they have less isolation. It's more likely that things are going to survive the trip there. And so we're going to find we're going to get a graph like this where we have this initially very high rate of arrival because it's not that hard to raft to that island. All right? But what's going to happen is the island is further away. That initial rate is going to be much lower. We're always going to go to 0 because eventually all the organisms that can make it there will make it there, and you can't have any more new species arriving from the mainland. But notice the difference is here, when I'm close, I have a high initial rate of arrival, and here I have a much lower initial rate of arrival. That tells me that this island is far from the mainland. It's more isolated. So if you're presented often on the AP test with a pair of graphs like this, you might be asked to say, well, comment on these islands in terms of, say, their isolation or their size. Well, in this case here, I only have information about isolation. We'll see in a minute how I get information about isolation, but I can look here and say, well, I know that this one has a higher initial rate of arrival, so it must be closer to the mainland than this one. So what I know then is that this one is close to the mainland because I have a high rate of arrival, and this one is further from the mainland because I have a lower rate of arrival. The reason I know this is about the arrival of new species is because that is always going to start high and drop to 0. Now let's look at how we can tell about area. So let me try to build up this thought for you for a second here, because this could be a little bit tricky to figure out. An island is basically limited on the number of species. I'm not talking about individuals. I'm talking about species that it can support. So let's just say that you bought this island and you said, you know what, I'm going to turn this into a zoo, kind of like Jurassic Park, but I'm going to use real world animals instead of these brought back dinosaurs. And so I'm going to start bringing new species over, introducing this island, and letting them begin reproducing on the island. And then I'm going to bring people over on boats, and they're going to enjoy my island zoo. I'm going to make all this money. What a great idea. And then you say, well, gosh, these people are not coming in this as much anymore because they've already seen these species. I'm going to bring some new species to my island. So you start bringing other species. Here's what you're going to find. That as I increase the number of species on the island, what's going to happen is as that rate at which I introduce new species goes up, so does the rate at which species that were already there go extinct, or the new ones go extinct. So the rate of extinction is going to go up. Why is that? Well, that's because we're going to have increased competition for the resources on the island. There's not going to be as much habitat available to the new species. There's going to be a lack of nesting space, increased disease, increased interaction between the other species. All these things combine to give us this absolute certainty. More species on the island means more extinction of species on the island. So let's make a graph of that. So instead of this being distance from the mainland, this is rather the rate of arrival. This is going to be the rate at which species go extinct. Now, if there's only one species on here, there's not much competition. It's likely to survive as long as the resources it needs are on the island. But as time goes by and I add species to the island, the rate at which species go extinct is going to begin to increase in a nonlinear fashion. And so if I make a graph, I'll see it look like this. So when you see this graph that starts at 0 and curves upwards to the right, this is about extinction. And again, on the AP test, they often won't say this. They'll just say rate. And they want you to be able to look at it and say, well, it makes sense that if I start at 0 and go up, this must be the rate of extinction, because if I have a small number of species, it's unlikely that they're going to cause each other to go extinct. But as I have more and more species on the island, they're going to put more pressure on each other and cause some of them to go extinct, largely through competitive exclusion. All right, so here you go. I have a large island here. A large island can support a lot of species, so I can have more biodiversity on this island. But a small island can support fewer organisms, so I'm going to have a higher rate of extinction and lower biodiversity. Big island, low rate of extinction. Small island, high rate of extinction. So when I look at this, I'll get a graph like this. And you're going to be asked to comment on either the isolation or the size. And when I look at this graph, this one doesn't tell me anything about isolation, because isolation would start high and go to 0. If it starts at 0 and goes upwards, that must be rate of extinction. So this isn't a graph of island size, it's a graph of rate of extinction, from which I can infer the size of the island. And here's why. A small island has a high rate of extinction. This red one must be a small island because it has a higher rate of extinction. And this one has a lower rate of extinction, so it must be a larger island. It's really easy to get yourself confused and say, oh, this one's big, so it must be a big island. No. The bigger the island is, the lower the rate of extinction. Now, another thing we sometimes have to do is determine how many species would we expect to find on the island. And so we have a plot of two aspects of the island. And notice I did what they do on the AP test. We just say rate. And it's up to you to understand, well, this one here, over here, what I'm talking about, this is a graph of rate of new arrivals, which starts high and goes to 0. And this is the rate of extinction, which starts at 0 and goes upwards to the right. So I look here and say, well, if I want to know how many are on here, I reach what's called the equilibrium point, where these two lines, where the line for arrival rate and the line for extinction rate cross, this is going to be how many species can be on the island. I call that the equilibrium point. And since it looks like on my number of species, which, by the way, if I haven't said so already, on these graphs, these two different types of graphs, the x-axis is always the number of species on the island. It looks to me like I'm counting by twos, so this should be 14. So I should find that this island can support 14 species. Often what you're going to find on the AP test is they're going to ask you to compare two islands. So here's island A, and here's island B, and they're going to ask us to compare them in certain ways. So maybe in terms of how far they are from the mainland, the size of the island, the number of the species. So let's walk through how you would do this. Okay, so the first thing you have to remember is that it's up to you to understand that this one here that starts high on the left and drops to 0, that's rate of arrival, and that tells you how isolated the island is. And the one that starts at 0 and moves upward to the right, that is the rate of extinction, and that's going to give you information about the size of the island. So let's just try this here. So I've got these two islands. They're definitely different from each other. So let's just see the first thing I say. I know that island A is closer to the mainland than island B. And the way I know that is I have a higher initial rate of arrival, which means it must be closer. And since this one has a lower one, it must be further. Then I can look and say, all right, well, I know island B must be larger. Why? Because it has a lower rate of extinction, meaning there's more area and habitat for the different species to live in. This has a very high rate of extinction, so it must be a much smaller island. And finally, I can look and I can tell you that island B has a greater number of species living on it, because if I look at the equilibrium point, it's located at about 21, almost 22, whereas here the equilibrium point is closer to maybe 17, it looks like. So there are other factors than just size and isolation of islands that can contribute to or inform us about the biodiversity of species on that island. Now, most of you will be asked about those two factors, isolation and island size, but there's other factors that can contribute to the biodiversity, and you should be prepared to comment on those things. So some of these things have to do with rates of evolution, primary succession, rates of productivity. So let's just see how that plays into it. So let's start with the age of the island. If an island is very young, remember, it comes up, it's just rock in the middle of the ocean. So primary succession is going to take time. So if I have an island that's just a few thousand years old, I would not expect much biodiversity there, because for the first few thousand years, it's just going to be slowly evolving enough soil to support species. So any arrivals that show up when it's just bare rock, they're just going to go extinct. So very young islands, I would expect to have lower biodiversity just because you haven't had a chance for primary succession to play out. Another thing is an older island, the more time that goes by, the more opportunity there is for endemic species to evolve. So those initial arrivals are, just those are ones that are concurrent with the same species on the mainland. Right? They're not different species. And usually in island biogeography, that's what we're talking about. But over time, those species are going to evolve. They're going to evolve to better fill the niches that exist on that island. Adaptive radiation is going to occur and end up with species on that island that don't exist anywhere else and can't wrap over the mainland because they don't exist on the mainland. So the older the island is, the more I would expect to have a higher proportion of endemic species. Another one is water temperature. So if you remember when we talked about the hydrologic cycle, warm water equals rising air equals rain equals productivity, and productivity equals higher biodiversity. So if I have warm water around my island, I would expect to have more rain, more plants, and more ability to support more organisms, more species. Similarly, latitude can play into this. So let's just keep the water temperature the same. At a higher latitude, I have, basically at a low latitude close to the equator, I'm going to have concentrated sunlight, which is good for productivity, which allows for higher biodiversity. But if I have that same island, everything else is the same, except we'll keep the water temperature the same. I'm going to move it up to a much higher latitude. Then what we're going to find is the sunlight becomes weak, the temperatures get lower on land, and I end up with lower biodiversity. All right, let's look at a couple examples and see how we do this. So I have two islands, island A and B. I see they both have basically the same area and the same amount of isolation from the continental mainland. But the difference is island A is 1 million years old and island B is 20 million years old. Well, that's more than enough time for primary succession to build the soils that we need to support any plant species that might want to live on these islands and might be able to get to these islands. So if we were asked, how does the number of species on A compare to B? I'd say, we've got the same area, so we're going to have the same rates of extinction, so we can probably support the same number of species. So I would think we're going to have the same number of species on both because they're the same size. All right. Now, what about the number of endemic species? Well, remember, evolution takes time, and this one's 20 million years old. So since this one has 19 million more years of evolution occurring, I would expect to have a considerably higher number of endemic species here than I would on this one here. Okay, let's try this one. Now what I have is two islands that are the same size, they have the same amount of isolation from the mainland, and they're the same age. The difference is island A is in a warm water ocean current, and island B is in a cold water ocean current. We definitely see this off the coast of the Americas. There's places where, like the Galapagos, where it's bathed in cold water, and there's other places where it's bathed in warm water. So on which of these two islands would I expect to find higher biodiversity? Well, the answer is I would expect to have higher biodiversity on island A because it's bathed in warm water. And the reason is warm water evaporates more. It causes convection. So I'm going to have warm, wet, rising air here, which is going to lead to precipitation here. Whereas over here, since the water is cold, I'm going to have sinking air and sunny skies, less precipitation. So more rain means more productivity, which means more ability to support more species and therefore higher biodiversity. And let's finish off with this. Now let's look at something that's not an actual physical island in the middle of the ocean. Now I have two forest fragments. When we talked about forest fragmentation in a previous episode, I have fragment A and fragment B. Now they both came from the same initial forest that got cut away in order to make farmland. So we're going to say both of these have equal isolation. And both A and B are all 5 kilometers away from the parent forest from which they were originally part of. So this is all farmland, 5 kilometers on the other side. So they have equal isolation. On which one of these would I expect to find higher biodiversity? And I think you know the answer. Well, the answer is going to be B. And the reason it's going to be B is it's a larger, quote, island, right? So it's because it's larger, it can support more species. It's easier for species to live there. They have less interactions. All the things that are true about physical islands are true about this fragmentation island. And so I'd expect to find more species on B. All right, so that's island biogeography. It's a cool topic, and hopefully you feel more confident about it going forward. Thanks for listening. Hey, thanks for watching. If you like this video, please go ahead and like this video. If there's something I do to make this better, or if there's another video you'd like me to make, please drop me a comment. You should probably check the description below because I do sometimes post problems that could help you do better on your AP test. And of course, you know it's coming. Please hit that subscribe button for me.